So hemoglobin's function, folks, is to deliver oxygen to tissues from the lungs. Its structure is similar to myoglobin, but different. Probably the biggest thing you can tell right off the bat, folks, is that this has quaternary structure. It is made up of 2 alpha and 2 beta subunits. It is kind of symmetrical across this line, so it has 180-degree symmetry. Now, if you looked at the primary structure of the different subunits, you would see that the amino acids are only about 18% the same compared to myoglobin. So 18%, not that similar. However, the tertiary structure of myoglobin and an individual subunit of hemoglobin is nearly identical. So this should tell us that their function is almost the same, and indeed it is. We know they both bind oxygen reversibly. Now, the major interactions between the various subunits are really between the alpha-beta subunits. So a lot of interactions between alpha-1, beta-1, and alpha-2, beta-2. Now, since we have this quaternary structure where the interfaces exclude water, we should assume that many of the interactions between the different subunits are hydrophobic, but of course there are going to be some hydrogen bonding interactions, some ion dipole, some ionic interactions as well. And when we think about hemoglobin, I always like to kind of simplify it in my mind, because thinking about all of the different atoms, even helices, becomes confusing. So this is how I like to think of hemoglobin. We have our 4 subunits that come together. In between all those subunits is a central cavity that's solvent filled, so water can get in there. And then each of those subunits also has its own heme molecule. And so this is kind of how I think about hemoglobin and kind of simplify it in my mind. We'll go into this in more detail in the next series of videos, but let's kind of introduce ourselves now to the structure of hemoglobin. So hemoglobin has 2 different structures that it can take. The T structure, deoxyhemoglobin, we generally think of T as inactive, or the R structure, oxyhemoglobin. We generally think of that as active. Cartoons of these 2 structures are at the right. What can we tell in terms of the difference between the T and the R state? Well, in the T state, we have very few interactions between alpha and alpha or beta and beta, because we have this very large central cavity with a lot of space there. Compared to the R state, you can see the central cavity is much smaller. Now let's talk briefly about this graph before going into more details about the R state and the T state. So hemoglobin, unlike myoglobin, has an S-shaped curve. So we can see here the S-shaped curve of hemoglobin compared to the hyperbolic curve of myoglobin. This S shape tells us that hemoglobin does cooperative binding. Cooperative binding means that when one subunit binds oxygen, this causes all other subunits to have increased affinity for oxygen. Or when one subunit binds oxygen, the others are more likely to do so as well. And we can actually see this happening in the graph. And we can see some of this T state, R state going on. So very early on in the graph, where the partial pressure of oxygen is very small, we can see the slope like this. Now let's compare this to what's happening at 40 torr, where the slope is more like this, right? The slope has increased. This indicates to us that we've gone from the T state of hemoglobin, where we're not binding oxygen well, to more of an R state, where we're able to bind oxygen and we're binding oxygen very tightly. So let's talk in more detail about what's happening in the R state and T state. Why does the R state bind oxygen well, and why doesn't the T state? And it really all comes down to what's happening at the heme. Quick reminders: T state does not bind oxygen, R state does bind oxygen. If you recall from the slides that I showed you, the heme is a conjugated system with many double bonds. Here's a quick look back at it, right? It has all of those double bonds. Conjugated systems should be flat because that's how they're most stable. sp2 hybridized, trigonal planar geometry. What happens in the T state is that heme is bent. So the conjugated system is bent. It's therefore not in an energetically favorable state, and it cannot bind oxygen. Let's take a look at that by drawing kind of cartoon versions. So here's the T state, here's the R state. In the T state, we have a bent heme with the iron in the middle. That heme, of course, is bonded to its ligand histidine, which comes from an R group in helix F. Now compare that to the R state. In the R state, the oxygen has come in and bound the iron. That pulls the heme into its lowest energy, most stable conformation, which is flat. And it now, since this conjugated system is flat, it has the good electronics to bind that oxygen well. This pulling of the heme to be flat pulls on that histidine, and of course on helix F. So we've kind of had this whole shift of the helix. Now I want to link this to cooperativity. I told you on a previous slide that the binding of a single oxygen leads the other subunits to be more likely to bind oxygen. Why is that? Well, folks, you should know that these proteins, right, are made up of peptides. So this heme, this histidine, this helix F are connected to the rest of the tertiary structure, right? If we imagine our hemoglobin cartoon as we've drawn it, if this, wow, that is not at all a rectangle that I wanted to draw. Try that again. If this is helix F, and it kind of moves, remember it's connected to all of the other alpha helices. So if we have movement at F, we have movement in the entire tertiary structure. And then let's not forget, this subunit interacts through its interface with this subunit. So movement in one subunit can be felt by the other subunits because they interact directly with each other at the interface. For example, here's a picture of just some of the interactions that happen in the T state and the R state and how different they are. So in the T state, we have this aspartate interacting with this tyrosine. But once we change into the R state, you can see that that tyrosine and aspartate no longer interact. And rather, we have new interactions between a different aspartate and an asparagine. So that's how cooperativity works in hemoglobin. Binding of just a single oxygen causes a local spatial change at the heme and helix F, but that's felt in the entire tertiary structure. And since we have interactions between subunits at the interface, one subunit kind of encourages the next to bind oxygen, and then the next, and then finally they all can bind oxygen. Lastly, folks, we're going to discuss a little bit about physiological environments that can impact the structure function of hemoglobin.